All right, welcome to chapter 10, day 4. And this chapter is on comparing two populations or groups with a mean and a proportion. But I'm going to spend a little bit of time going over the differences and similarities and things like that between one sample means and one sample proportions with two sample means and two sample proportions. I think that's important to do in this chart. And again, feel free to stop the video at any time to copy the notes down. This is a really long video. I'm going to be going through way more than I have to, but I really want to compare the single mean tests with the double mean test, the single proportion test with the double proportion test, as well as make sure I cover confidence intervals for the double mean and double proportion. So there's going to be a lot going on here, so you're going to have to stop the video periodically to do that. Okay, so we learned previously about comparing a single mean or a single proportion to a known reference number, okay? And our notation for the means, the parameter is mu, and this is x bar. Of course, we don't write the word bar, we write x bar. I'm going to get a different color here. There we go, x bar. And then instead of, you can use pi, p, or pi, and p hat is, of course, p hat, okay? All right, so the standard error, standard deviation for the mean is s over the square root of n. And for the proportion, for the single proportion, it's p times 1 minus p, often called q, over n, all square rooted, okay? The critical value, that t star number that you find on the chart, that's going to be n minus 1, the sample size minus 1. And for the proportion, it's going to be that bottom number on the chart, which is called z star. All right, here's how you calculate your p-value. Although most likely you're doing this on your calculator by doing a t-test, most likely. And I'm going to be going through that as well. But if you did it by hand, it would be your statistic, which is x bar, minus the mean, which is that center number called the reference number. That's in the problem, divided by s over the square root of n. And then that's going to tell you how far your statistic is away from the center of the curve. And then you'll be converting that to a p-value, okay? For the proportion, it's going to be a z. It's going to be your statistic, which is p hat, minus the center of that curve, which is the reference proportion, whatever that is being compared to, over p, 1 minus p, often called q, over n. Now, instead, if you did real quick, let's go back to this. You're probably going to be calculating this by doing a 1 prop z test on your calculator. That's most likely what you're going to be doing. You're probably not going to do it by hand. When I show you the models later of the two sample tests, they're going to be done by hand, and then I'll go back and do them on the calculator, which makes this video very long, okay? All right, for the confidence interval, to develop that, and again, you're looking for the reference number being in here or not in here. That's going to be x bar plus or minus t star times s over n. And again, you're probably going to do it with the t interval function on the calculator, would be my guess. Most of my classes have Texas Instrument calculators, and that's their verbiage. All right, and on this one, it's going to be p hat plus or minus z star times p, 1 minus p, called q, over n, and that's probably going to be done on the Texas Instrument calculator, 1 prop z, and I think it just says int, but it stands for interval, 1 prop z interval, okay? That's a review of stuff you should know previously. Then in this chapter, we got into two sample tests where you're comparing two samples, could be a mean, could be a proportion, and wondering are they the same or different, or is one greater than the other, or is one less than the other, okay? And we know about two-sided and one-sided. A two-sided test is when it's not equal to. You're wondering if they're different, because they can be different where one is much bigger or one is much smaller. And then there's one-sided tests. And one-sided tests are greater than and less than. And those are only shaded on one side because you're only wondering if mu1 is greater than mu2 or if mu1 is less than mu2. That's called a one-sided test. Now be careful. You got two sample tests and you got two-sided tests. So a two-sample test is a double mean or a double proportion, and then a two-sided test would be a not equal to test. So don't confuse those terms. You could have a two-sample one-sided test where it's two proportions that are being compared, but it's only one side you're concerned about. Is proportion 1 greater than proportion 2? Okay? All right, so let me slide this up. Okay, so here is one-sided and two-sided tests, okay? Just as a reminder, and I went over that verbally, but your one-sided test will be greater than or less than, whether it's a mean or a proportion. And I like to use pi on this. I typically like to use pi and mu. I like to use the Greek symbols for the parameters, but you don't have to. You can just use p. And the two-sided tests are greater than, not equal to and not equal to. And you can see you'll be shading on both sides of them. So when you find the p-value by hand on something like this, if you're doing a one-sided test, on the calculator, this would be done by doing, for a mean, it would be t-CDF, and you would type in your t-score. Let's say it's 2.1, and if I want greater than, I'm going to put infinity, and then I'm going to put my degrees of freedom. Let's say there were 9 samples, so my degrees of freedom is 8. So I'm going to type in an 8, and that's going to spit out a p-value. Now, if you want it to be two-sided, you just have to multiply by 2 to get that. Now, if you're doing a proportion, that's going to be NCDF, and that's going to be, let's say you got the same z-score, 2.1 comma infinity for a greater than 1. And then if you want it two-sided, you're just going to multiply by 2 on your calculator. But again, most likely you're probably going to be using the calculator function to do the tests anyway, so you're going to avoid this. But I think it's good to know by hand, just in case you get into a situation where the problem is worded in such a way where you'll have to do it by hand, because they can be very clever with that. Okay, now in your confidence intervals, for your critical value, if it's a one-sided test, and let's say alpha is 5%, then if you want to get the same confidence interval, if alpha is 5%, you're going to multiply it by 2 to make it two-sided, and it'll be a 90% interval. Now, if alpha is 5% and it's already a two-sided test, that means 2.5% was put on each side already. It's just going to be a straight 95, which will be 100 minus your alpha level. Okay? So there's your one-sided and two-sided stuff. I said that a couple times. Now, don't confuse two-sided with two-sample. Okay? Totally different concepts. Two-sided is the shading on each side, but two-sample is what this particular chapter has been about. So all of this is essentially review. All right, so let me slide this up again so we can see the next part. Okay, so two-sample inference tests. When we're dealing with two distinct populations. Okay. Now this is how you're going to get the p-value of that. You're going to do x bar 1 minus x bar 2 minus 0 divided by the standard deviation. But in reality, what you're probably going to do is you're going to go to two sample test on your calculator, probably. And then you're going to have a drawing here in your notes, and 0 on the 2 sample tests always goes in the middle. And then, of course, you put your standard deviation here. And then whatever the difference is between the 2 means are, let's say that one mean averages 15 and the other mean averages 10, then the difference is 5. That's going to be out here. And then you're probably just going to punch it in on your calculator, and the calculator is going to give you the t-score and the p-value automatically. It's doubtful that you're going to go this route, but you're going to go ahead and put 0 there, put the difference between the 2 means wherever that belongs, write the standard deviation here, and I'm going to be doing all this for you when we get into this, okay? This is just a preview, okay? Now here's your confidence interval. And again, you need to know how to write the confidence interval out for the 2 sample tests. It's the difference between the 2 x bars plus or minus t star. Now what you use for t star is n minus 1 of the smaller sample. So if they have different sample sizes, take the smaller sample and subtract 1, okay? And then again, you write the Pythagorean theorem essentially to combine the deviations for the 2 means, okay? Again, most likely to calculate this, you're going to do a 2 sample t interval, probably to calculate it, but please write that out and then let the calculator do the calculations for you. Okay, for the proportions, it's the same idea. For the proportions, what you got is the difference between the 2 proportions minus 0. By the way, when you subtract 0, there's nothing to do. It's just the difference between the 2 proportions divided by the standard deviation of the combination of them, which again is more or less Pythagorean. But again, most likely, you're going to be using the calculator. And that's going to be a 2 prop z test on your calculator, 2 prop z test, okay? Now, prop is obviously proportion. And again, what you're going to be doing is you're going to be putting 0 in the middle, because 0 is the HO in this case, meaning there is no difference between the 2 populations. And then you're going to write the difference, whatever this difference is, you're going to write it. Let's say 1 is 0.25 and 1 is 0.23. Well, then the difference is 0.2, okay? And then you're going to write the standard deviation, this, right out here. And I'm going to be doing this for you, okay? Okay, so, and then for the confidence interval, it's very similar. The difference between the 2 sample proportions, plus or minus z star, that's the bottom of the page, multiplied by the standard deviations that are combined, which is again Pythagorean. But again, after you write this out, you're most likely going to be going to 2 prop z interval on your calculator. That's probably what you're going to be doing, okay? All right, so far I'm just giving you all the background to this. Now, the key changes from the 1 sample to the 2 sample is you're going to have 2 parameters for statistics. In your requirements, you've got to mention both. And the degrees of freedom that I mentioned before, it's a smaller sample size minus 1. Okay. Now, when you get these problems, the first thing you're going to ask yourself is this a mean or a proportion? Then you're going to ask yourself, is this 1 sample or 2, or is it a matched pair? Now, a matched pair goes back to a 1 sample. That's what you're going to be asking yourself right away. Now, in the samples that I have 4 examples. They are all 2 sample tests because we're in the 2 sample area, but I'm still going to be going through that process of asking myself those questions. All right, now, there are 3 sentence frames you should be familiar with, okay? One of them is the interpreting the meaning of the p-value. Now, the p-value assumes HO is true, okay? So, if HO is true, and you can write that out in terms of the problem, then let's make up a percent, then 5% of all samples would produce the observed results in this sample, or more extreme, okay? So that's something you should know. The meaning of the confidence interval itself, just the meaning of the interval, okay? If the process is repeated many times in the same manner, then approximately 95% of the intervals would produce or capture the true mean, the true proportion, the true difference of the two means, the true difference of the two proportions. You can say whichever one of those four it is, okay? And then your conclusion. I'm going to slide this up so you can see the conclusion a little bit better, okay? Okay, so the conclusions. If you're using a p-value, it's going to be reject HO if the p-value is less than alpha. And then you'll say, we have significant evidence to suggest whatever HA is. If you're using a confidence interval, if the interval did not capture the parameter, which is 0 in this case for a two-sample test, then you would say the confidence interval did not capture 0, therefore we have significant evidence to suggest. Now, for a fail to reject, if the p-value is greater than alpha, we will fail to reject HO because we do not have sufficient evidence to suggest whatever HA is, or if the interval did capture 0 for a two-sample or for a matched pair, okay? On the one sample, if you remember, it's the reference number, whatever that is, okay? So the confidence interval did capture 0, therefore we have insufficient evidence to suggest whatever HA is. Okay, that's all the background. Now we're going to do 4 problems, A, B, C, and D. And all 4 of them, I have some sentence frames, and it's all written out previously. And I'm going to be going through this, and then I'm going to stop and use the calculator as well. So this is going to take some time. So feel free to stop this whenever you need to, okay? Okay, let's look at this. I'll reread question A here. Does living on campus in college truly help a student's GPA? There are some studies that say it does. A study at another university found that 31 randomly selected students, who live on campus, had a GPA of 2.93 with a standard deviation of 0.42. While 40 randomly selected off-campus students had a 2.88 average with a standard deviation of 0.84. So that's a little bit bigger than this. But is that big enough to suggest that we have a difference overall in kids living on campus? I don't know. And that's the question. Is there evidence to suggest that on-campus students have a higher GPA? All right, the first thing you do when you get a question like this and you realize it's a significance test is you're going to ask yourself, is this a mean or is this a proportion? And this is clearly a mean because you're talking about a GPA of 2.93. This is not a percentage. And the second question, is this a one sample test or a two sample test or a matched pair? Well, one has 40 randomly selected students, one has 31, so this can't be a matched pair. This has got to be 2 separate independent samples. I have a 2-sample mean test, okay? Or a 2-sample t-test, I should say. 2-sample t-test. All right, fine. Now there's a couple of ways you can write your HOHA, okay? You can write it where the 0 appears and you see the middle of that curve. Okay, and this is the mean of on-campus students minus the mean of off-campus students is equal to 0. Is there no difference? Or is the mean of on-campus students minus the mean of off-campus students greater than 0? Okay, because that's what they want to know. Now, I would probably write it like this, and this is how your calculator wants it. okay? I'm going to do mu sub on is equal to mu sub off. Okay, I guess I should put on there. They're both O's, okay? And then HA would be mu sub on is greater than mu sub off. All right? Now this is how the calculator is going to take it. This is often how I write it, but you can write it this way too. It's not that big a deal to write it either way. Okay, but the 0 doesn't appear then for the middle of the curve. Okay, let's go through our assumptions. One assumption is we have a representative sample of both on and off-campus students. Great. Okay, and again, this is the acronym SPIN that we go through constantly. Okay, the population size is at least 10 times 10n, so I'm going to go 31 times 10 and get 310, and I'm going to go 10 times 40 and get 400. So I'm assuming that there's at least 310 on-campus students and 400 off-campus students. And again, in a small college, that could be a question, but most colleges are going to have that many kids. Okay. Each GPA is independent. Great. And then do we have enough sample size for a normal curve? Sure. Because 31 is bigger than 30, and 440 is bigger than 30 as well. I don't know what this 10 is for, but so therefore we're going to have a normal curve due to the central limit theorem. All right, this next spot here, okay, this next spot, I'm going to move the video up so we can see it, the notes up so you can see it. Okay, it's fairly unlikely that you're going to do it in this manner, but let me go through this. How to get a T-score or a standard score, okay? So the first thing is you notice the difference between the sample GPAs is 0.05, okay? So 2.93 minus 2.88 minus 0 is 0.05, okay? Then I combine the standard deviations in a Pythagorean way. You actually never have to calculate this, just have to write it out, okay? And if you did all this by hand, which would be crazy, you would get a T-score of 0.327. Then after that, you would go ahead and type it into TCDF, okay? And that would be a T-score of 0.327, comma, infinity, because it's a greater than problem. And the degrees of freedom would be 30. It would be the smaller sample size minus 1. And if you type that in your calculator, you're going to get a p-value of 0.373, which is way bigger than alpha. Okay? So let me stop here, and I'm going to bring up the notes, and I'm going to do this part on the calculator, which is much more likely the way you're going to do it. Okay? So let me go ahead and do that. Okay, so more than likely, what you're going to do in this part right here to do your test statistic, it's almost assured you're going to do this. You're not going to go the by hand way, but I think it's important to see that. Is you're going to draw out our traditional graph. Raw score, z-score, percentile, okay? So you got the 0 there, which represents no difference between the two GPAs. Then you're going to set up your standard deviation. But when you set up the standard deviation, you're never actually going to calculate it. 0.42 squared over 31 plus 0.84 squared over 40. You're just going to leave it there. Now, the difference between the two means was 0.05. If you remember, it was 2.93 minus 2.88. That's 0.05. I'm just going to write 0.05 as the difference from the x bars. So once you have that set up, you're going to go to your calculator, okay? And you're going to be able to calculate, it's not a z-score, it's a t-score. you're going to calculate a t-score and a p-value automatically from your calculator, okay? So I'm going to go to the calculator now. We're going to do that, and then we'll come back to this, okay? All right, so on your calculator, you're going to go stat and you're going to arrow over to tests, and you're going to find your test. It's not a t-test, that's a one sample. It's a two sample t-test right there. Okay? And then I'm going to type in the first X bar, and the first X bar was the on-campus kids. Okay? And the on-campus kids had an average of 2.93. Their standard deviation was, I believe, 0.42. Just type that in. And they had 31 kids in the sample. The second group had a mean of 2.88 with a standard deviation of 0.84, and then they had 40 kids in their sample. Okay? Now I'm going to come down here, and I have my three choices. What's flashing is the two-sided test, which I don't want. I want greater than, because the way I set it up, it was, following the cursor here, is the on-campus kids, X bar 1, greater than X bar 2, the off-campus kids. So I'm going to leave it there. It's going to ask you about pooled. You pool when the standard deviations are the same. They are not, so I'm not going to pool. And I'm going to go ahead and draw it. I really like drawing it, okay? And there we go, okay? Notice it gives me a t-score and a p-value. 0.3273 is the t-score, and the p-value is 37.23%. All right, so let me go back now, and I'm going to go ahead and write these on the screen, okay? So that's really all you have to do, so you don't have to go through all the fancy calculations. You end up with a t-score of 0.327, but I'm going to round that to 0.33. And then the p-value is 0.373. I always tell kids to circle the p-value because it's kind of the answer. Now, let me go through some sentence frames here with you, okay? Real quick. What does this p-value mean what's the p-value mean? There's a 37.3% chance that we would get data this extreme even if the two groups were equal. So this could have easily happened by chance, okay? For my conclusion, I would say fail to reject HO at alpha 05 because the p-value is greater than alpha. We have insufficient evidence to conclude that the on-campus kids have a higher GPA than the off-campus kids. That would be how that works using this, the test method. Now I'm going to go back to the scripted notes, the answer key, and we're going to look at the confidence interval for this. Okay, so for the confidence interval, we are looking at this area right here. Okay, I'm going to highlight that. This is what we're looking at. Okay, so now the reason why I chose a 90% interval is because I did an alpha 05. And because this is a one-sided test, because it was greater than, I double alpha and make it a two-sided, 10%, and then go 100 minus that and get 90%. All right, now, this is my statistic. This is 0.05. And you need to write this part out, but you wouldn't calculate it by hand, okay? This number comes from 90% degrees of freedom 30 on the chart. And then this is the standard deviation. So no problem, Okay, this is pretty easy to do. So you would write this out on your test, and then you're going to go to the calculator to calculate it. So let me go ahead and send this over to the calculator to do that, okay? All right. Get rid of the chart here. All right, stat, tests, and I'm going to go to sample t test. To sample t interval, to sample t interval. All right, no problem. The data is probably in there, and it is, because the to sample t interval knows it's related to the to sample t test. So I'm going to go through the menu. It's probably going to ask me about pooled again. And I want an interval of 90. I got lucky on that. Pooled, no. I'm going to go ahead and calculate this. Okay. If you notice, one of the intervals is negative and one of them is positive. And what this literally means is that it's possible that the off-campus kids have a higher GPA than the on-campus kids by about 0.2. Or the on-campus kids have a higher GPA than the off-campus by 0.3. But the main thing you're looking for is the reference number in this problem. And for matched pairs, and two mean tests and two proportion tests, the reference number is always 0. Is 0 in that interval? Yes, it is. And that means that there is very possibly no difference between off-campus and on-campus and off-campus GPAs. There's probably absolutely no difference, or close to no difference. And this is why we have a fail to reject HO. So let's go back to the notes here so we can see that. Okay, so there's that number right there. Now, and what you would write on the conclusion on this is, because the interval captured 0, we have insufficient evidence to conclude that the on-campus students have a higher GPA than the off-campus students. Okay, question B. And I changed the names from Verizon to Verizon and AT&T to AA&T. You'll get the idea. Is Verizon's customer service better than AT&T? A sample of 25 Verizon customers showed a 60% satisfaction rating, while 50 AT&T customers showed a 58% satisfaction rating. Those are awfully close together. I mean, do you really think those are significantly different? I doubt it. Okay, let's do the math. Is there evidence to suggest that Verizon's customers are more satisfied with their service? All right, the first thing you're going to ask yourself, is this a mean or a proportion? This is a proportion, clearly, because we're dealing with two percentages, okay? And then you're going to ask yourself, is this one sample or is this two? Well, it's obviously two different samples, a group of 25 Verizon users and a group of 50 AT&T users. Okay, so here's your hypothesis, and we're wondering if Verizon's are more satisfied. More satisfied is a greater than symbol, okay? And it's going to be 0 right there. It's going to be a greater than symbol. So what I wrote is P, the true proportion of Verizon, minus the true proportion of AT&T is equal to 0, meaning there's no difference. And it's very possible there's no difference. They look awfully close. And then the true proportion of Verizon minus the true proportion of AT&T is greater than 0 to match the problem, okay? Now, most likely, I would have written HO this way, most likely. Pi sub Verizon is equal to pi sub AT&T. And then here, I'm going to write for HA, I'm going to write pi sub Verizon is greater than pi sub AT&T. That's probably how I would write it, and that's going to match how you're going to do it on the calculator. Whether you use P or pi doesn't matter. I just prefer pi because it matches the Greek symbols that usually stand for the parameters or population notation. Okay? Fine. Now, let's go through our assumptions, and it's got to be done in plural because it's two samples. Assume that, 1, we have a representative sample of both Verizon and AT&T customers. 2, this is the 10% rule now. Assume the population is at least 10 times n, meaning the population is greater than 250 for Verizon and greater than 500 for AT&T. Assume that each satisfaction rating is independent. And then this is the hard one here. Assume the sample size is large enough. You got to do NP and N1 minus P twice for both of them. And it's kind of hard to read here, so I'm going to write it again right here. So you're going to go for Verizon, 25 times P, 0.6 is greater than 10. And then 25 times 0.4, which is 1 minus P, that's greater than 10, okay? And then you got to write it twice. You got to do it again for the AT&T one, okay? And I'll do that here. I'm going to go 50 times 0.58 is greater than 10, and 50 times 0.42 is greater than 10, okay? And that encompasses that particular one. It's a little bit hard to read here. Okay, so that's step 2. Step 1, HOHA. Step 2, the requirements. Step 3 is to develop the test statistic. You are most likely going to be doing this on the calculator, not here. But I'm going to show you the long way. This is the long way to do it, okay? What you're going to do is take the difference. The difference is 0.02 between 60% and 58%. 0.02. Subtracting 0 is the same thing. So the difference is 0.02. And then you're going to divide it by the standard deviation of the statistic, which is P, 1 minus P over N added to the other one, okay? And again, it's very unlikely you'll do this by hand. It's a pain to do. And that z-score comes out 0.17 if you round. And then if you're going to turn that into a p-value, if you did it by hand, you are most likely going to do NCDF 0.166 comma infinity. Probably put 100 in for that on your calculator. And that's going to get you an answer of 0.4341. And that answer is very large. So let's go over the meaning of what that means, that p-value. There is I'm going to round this to 43%. There is a 43% that we would get data this extreme even if there is no difference in satisfaction rating. So in other words, this difference of 0.02 could very well have happened by chance. There probably isn't a difference, okay? The conclusion on this would be fail to reject HO at alpha, let's say I did 0.5, okay? Because the p-value is greater than alpha. We have insufficient evidence to suggest that Verizon's customers are more satisfied with their service, okay? All right, so I'm gonna go ahead and go over to the calculator now. Well, actually, let me do this. Let me go ahead and draw up how you're probably going to do this part by hand, okay? Okay, so most likely you're going to do this on the calculator, and so you'll be required to draw up how this would work. What goes in the middle, of course, is 0, because 0 represents there's no difference between the satisfaction ratings. And then here, all you're going to do is draw out the standard deviation. You're not going to calculate it. So it's 0.6, 0.4 over, let's see here, oh, what was that? I think it's over 25, and then 0.5, 0.8 over 50. Okay, 0.5, 0.8 over 50. Okay. I think I actually had the wrong numbers in the other one. I think I had the numbers from part A in part B, just so you know. So I gotta flip over and switch that. Okay. All right. And then once you get that, you're gonna let the calculator do the work. And this is going to be a 2-prop. Try that again. 2-prop Z test. Okay, we're going to do a 2-prop Z test. Okay, so I'm going to go ahead and turn this off. Okay, I'm going to click off on this, and I'm going to go to the calculator. Okay. Okay, so for the 2-prop Z test, you're going to go stat tests, and then you're going to go 2-prop Z test. All right? And for X1, it was 60% of 25. So I'm going to multiply 0.6 times 25. Okay? And that comes out 15. And this 25 is the n. And for X2, I'm going to multiply 0.58 times 50 to get the n there. And that's 29 out of 50. So, and then it's greater than is that, and I'm going to go ahead and draw this out. And there you go. There's your z-score, and there's your p-value. It's about 0.17. And there's your p-value. Okay? Okay, so let me go through now, and I'm going to draw out by hand. I'm going to do this same exact problem as if you did it with a confidence interval. Okay, so let's say you did a confidence interval with this. The statistic is 0.6 minus 0.58. Some people would just write 0.02. That's fine. Plus or minus. And let's say I did a 90% confidence interval. So if my alpha was 0.5, this would be a 90% interval because this is a one-sided test. So I have to double 0.5 to make it two-sided, make it 90%, and then go 100 minus so that I can get 90%. And 90% for a z-score on the chart is 1.645, okay? And then I'm going to multiply that out with this standard deviation, which is 0.6, 0.4 over 25 plus 0.58, 0.42 over 50, okay? And once you have that, you're going to write that down, but you're going to let the calculator do the calculations, okay? So let me pause this, and I'm going to go over to I'm going to turn this off, and I'm going to go over to the calculator to finish it, okay? All right. So I'm going to go stat tests, and I'm going to do a 2-prop z interval. And the numbers are probably in there, and they are, because the calculator knows that the 2-prop z interval is related to the 2-prop z test. And I'm going to go ahead and go to calculate here, all right? And there we go. Okay, so what do these numbers mean? Negative 0.17 means that AT&T may actually be preferred better than Verizon up to about 18%. And this one, 0.22, let's say, could mean that Verizon is could be favored as much as 22%. This is a really super wide interval, mainly because the sample sizes were so very small. But the main point here is that 0 is in the interval, meaning it's very possible that there is no or very little difference between the two businesses' satisfaction ratings. Okay? So your conclusion would be fail to reject HO because 0 is in the interval. We have insufficient evidence to suggest that Verizon's customers are more satisfied than AT&T with their service. Okay? Let's go on to item C. Okay, item C. Do men and women have different body temperatures? Okay? A sample of 34 men and 32 women found that the average body temperatures were 98.9 for guys and 98.4 for women. That's just a little bit of a difference. With a very small standard deviation, this could be a big factor, of 0.2 for the guys, 0.3 for the girls, respectively. Is there evidence to suggest that temperatures are different? Different is the two-sided symbol of not equal to, okay? So here's how you're going to write your HOHA. Mu sub men minus mu sub women is 0. Mu sub men minus mu sub women is not 0, okay? I should also point out, the first thing I should have done is ask myself, is this a mean or is this a proportion? And this is clearly a mean. These numbers aren't percentages. They are whole numbers, so they're means. Okay? Is this one sample or two? It's two samples because you're talking about men and women. There's no matched pair here. Okay? All right. Now, again, most likely you're going to write this differently. You're probably going to write HO as mu sub men equals mu sub women, meaning their temperatures are the same. And then mu sub men is not the same as mu sub women. Their temperatures are different, okay? Your assumptions, and once again, I always point out it's the SPIN acronym to remember, but don't write that, just write the bullet points. Assume that we have a representative sample of both men and women. Assume the population size is at least 10 times the sample there. So the men would be 340 and women 320. Of course, there's way more than that, okay? Assume each body temperature is independent, and then both of the sample sizes are sufficiently large to invoke the CLT, or central limit theorem, meaning that we're going to have a normal curve because the men and the women are both over 30, and 30 has been deemed the magic number where you'll have a normal curve of the sampling distribution, okay? All right, the test statistic. Once again, on the test statistic, it's very unlikely, it's very unlikely that you're going to do this by hand, but I still want to show it to you. The difference between the two temperatures is 0.5. That doesn't sound like a lot, but it actually is when you start involving how small the sample, the standard deviation is, okay? So 0.5, and we're going to divide that by the standard deviation, okay? And when you get the t-score, it's off the chart tiny. It's 7.92. And then when you get that into a p-value, you get essentially 0. This is 6.16 times 10 to the negative 9th. And that's essentially 0. So probably when you, to convert the t-score to the p-value, you're probably going to use t-CDF if you did this by hand. And you're going to type in the t-score, 7.917 under the whole thing, comma infinity, comma degrees of freedom 30, degrees of freedom 31, I should say, 31, The chart, you'll have to go to, it's the reason we're 31. If you did it by hand, the chart would have to give you 30 because it doesn't have a 31. Now, when you get that, you got to multiply the answer by 2 because it's two-sided. But it's highly unlikely you're going to go this direction. Okay, you're probably going to go the direction of doing this on the calculator. So let me first set this up, set this problem up by drawing it out, okay? So most likely you're going to go right here, and you're going to put 0 there because 0 represents that there's no difference in the body temperatures. Then you're going to make your standard deviation, okay? You're not going to calculate it, you're just going to draw it up. And that's going to be 0.2 squared over 34 plus 0.3 squared over 32, okay? Great. And you're going to leave it, all right? And now the typical difference was, I believe it was 0.5, okay? The typical difference is 0.5. There is a little bit of a difference there. And I got this by going 98.9 minus 98.4. No problem. That's how I got that 0.5. And now I'm going to put it in the calculator, and I'm going to let it get the t-score and the p-value for me, okay? Okay, so I'm going to go stat, tests, and I'm going to go to 2 sample t tests, okay? And x bar 1 is 98.9. Standard deviation is 0.2. X bar, and the n on that was 34. For the girls, it was 90. No, for the boys, I mean. No, the girls was 98.4 with a standard deviation of 0.3, and there were 32 samples. Okay, got it. All right, and it's going to ask me, I want a two-sided test, so it's not equal to. Then I'm going to pooled, no. The standard deviations are close, but we're not going to pool them until they're identical. And then I go ahead and hit draw on this. And it gives me the p-value of 7.92, and then the t-score of 7.92. The p-value is 0. And what it did is it didn't do all the e to the whatever, it's just 0. So what does that p-value mean? That p-value means there's essentially no chance that we would get data this different by chance alone if their body temperatures were the same. They're not the same. Men are probably running a little bit warmer than women on average for whatever reason, okay? The conclusion on this would be reject HO at alpha 0.5, I'll pick 0.5 again, because the p-value is less than alpha. We have sufficient evidence to suggest that the body temperatures for men and women are different. So let me go back over to the drawing here. Let me go back over to the drawing, and you would simply type in your t-score, 7.92, and your p-value, essentially 0. I like to put the word essentially. And then you can put your conclusion there. Okay? So, now, what if you did this with a confidence interval instead of a test? No problem at all. If you did it with a confidence interval, I'm going to do a 95% confidence interval. And the reason I'm going to do a 95% confidence interval is that my alpha was 0.5. And this is a two-sided test already. so I don't have to double it. I'm just going to go 100 minus alpha, and I've got my 95% confidence interval, okay? All right, so I'm going to be writing down my statistic, which is 98.9, what's that? Minus 98.4, plus or minus, all right, do plus or minus, I'm going to find 95% on my chart at degrees of freedom 30, because there isn't a degrees of freedom 31 on the chart. It's got to go to 30. So that's going to be 2.042, and I'm going to multiply that by the standard deviation of 0.2 squared over 34 plus 0.3 squared over 32. Okay? Now, again, after you write this, you are very unlikely to calculate this by hand. You're probably going to go to the calculator. So let me do that. Let me erase this and let me go to the calculator. Okay? So on the calculator, I'm going to go stat, tests, and I'm going to go to 2 sample t interval. 2 sample t interval, because this is a mean. 2 sample t interval. And of course they're in there because the calculator knows the relationship between a 2 sample t interval and a 2 sample t test. Okay, so I'll just walk through this real quick. 98.9 is the guy's temperature. There's the guy's standard deviation that's flashing. And there was the sample size of 34. There's the girl's temperature. There is the girl's standard deviation. And there is the girl's sample size. Confidence level, I'm going to go 95 this time. And pooled, no. And I'm going to hit calculate, and it's going to give me my answer. All right. So this is a pretty tight interval. Basically what it's saying is that the two temperatures for guys and women are different. It could be as low as about 0.4 degrees or as high as 0.6. But the main thing is that 0 is not in the interval. It's not anywhere close to the interval. So your conclusion, if you were to write it, would be reject HO at alpha 05 because 0 is not in the interval. We have significant evidence to suggest that the temperatures of men and women are different. Okay? All right. Let's go to the last problem of the day, or of this session. Okay, the last problem of this session, let me go over to the notes one. Okay. Do those who eat meat have a higher chance of developing cancer? A lot of vegetarians out there, and they believe that. There is some evidence to that, I think, over time. A study of 43 randomly selected meat eaters had a 13% cancer rate, while 26 randomly selected had a 9% cancer rate. Does this suggest that those who meat eat have a higher chance of developing cancer? All right. A couple things at play here. One is this is actually a pretty big difference. But the problem is the study was done on such a small sample size that I got a feeling this is not going to prove anything or suggest anything. But let's go through it, okay? The first thing you're going to ask yourself, as always, is this a mean or a proportion? And this is a proportion. We have percents. Is this one sample or two? It's definitely two different groups of people. So this is a 2 proportion z-test, a 2 prop z-test, or a 2 prop z interval. Okay, so your hypotheses, M is meat eaters and V is vegetarians. So the percentage of meat eaters minus the percentage of vegetarians is the same in terms of cancer rate. And then here, and this is going to be greater than 0 here. And then the percentage of meat eaters minus the percentage or proportion of vegetarians is greater than 0. And once again, you're probably not going to write it this way. You're probably going to say, and I like to use pi sub meat eaters is the same as pi sub vegetarians, okay? And then HA is pi sub meat eaters is greater than pi sub vegetarians. We got a one-sided test. This is a two-sample but one-sided test, okay? Let's go through our assumptions real quick. We have a representative sample of both meat eaters and vegetarians. We didn't violate the 10% rule because there's certainly more than 430 meat eaters and more than 260 vegetarians out there. Each cancer status is independent. And then you got to do your NP greater than 10 and N1 minus P greater than 10. You got to do that a couple of times, okay? And that's a little bit of a pain, but I'll go ahead and do that for you. So, so we're going to go 43 times 0.13. That's greater than 10, we hope, okay? One of these is actually not bigger than 10. And then 43 times 0.87, that's greater than 10. And then 26 times 0.09 greater than 10. This one is not greater than 10. So this study actually suffers from a lack of sample size. So we probably wouldn't even want to go through with the study until we got more samples. I was suspicious of that right away. But for the purposes of this particular video, we're going to go ahead and finish it. And then 26 times 0.91 greater than 10. On a test of like an AP test, they wouldn't give you this. They would ask you, do you meet the criteria, yes or no? Do not perform the test. They would say something like that. But for this, we're going to point it out that we didn't meet the sample size requirements, but we're still going to proceed anyways, like I'm saying, okay? Proceed with caution is my official term. Okay. All right, as we've talked about a million times, this is how you would get the t-score and the p-value. You're unlikely to do this way. You're probably going to go off the calculator, but you're going to have 13% minus 9%, which is 4%, 0.04. That is your test statistic, minus 0, same thing. And then this is the Pythagorean equivalent here for the standard deviation, okay? 0.13 times 0.87 over 43 plus 0.09 times 0.91 over 26 square root. And that's going to be your how you get your t-score, okay? Your z-score. This is the proportion. Your z-score is 0.526. Now again, to convert 0.526 to this is a couple of ways, but you could use NCDF and type in 0.526 comma infinity, and you're going to get the p-value of 0.299. Now, you're probably going to do a different way. So let's one more time. Let's go ahead and do this differently. Okay. We're doing this problem right here, but I'm going to move it over here, okay? So what we got here on this problem is the 0 is if there's no difference. We have a 4% difference, okay? And that ends up being 0.04. Now, how did I get 0.04? I got that by going 13% minus 9%, okay? And then the standard deviation is going to be written right here, okay? And that is pretty easy to write. That is, let me erase this a little bit here. That is 0.13 times 0.87 over 43 plus 0.09 times 0.91 over 26. I wouldn't calculate that. I would just write it and leave it on your paper and then go ahead and let the calculator finish it off. Okay, so let's do this. Okay, so that's kind of in the way. I'm going to go ahead and erase this. Okay, so you're going to go stat tests, and you're going to go to 2 prop z interval. All right, so we've got to do a little calculations here to get this. The first one is 13% of 43, so I'm going to go 43 times 0.13. And then ends up being 5.59, which is actually around 6. Okay? And that is out of 43. And on the second one, I'm going to go 26 times 0.09. And I'm going to get 2.34. That's around 2. So I'm losing a little value here on this. And then this is 26. All right. And we are going to do a 90% interval because I've consistently done 0.5 for alpha. And this is a one-sided test because it's greater than. I have to double alpha from 0.5 to 10% and then go 100 minus. Okay, and I calculate this and I get something like that. Okay? So there's my confidence interval that I got, okay? In any event, as you see, I lost value on some of this stuff, but that's okay. So is 0 in the interval? Absolutely 0 is in the interval. So our conclusion is to fail to reject HO because 0 is in the interval. We have insufficient evidence to suggest that meat eaters have a higher cancer rate than vegetarians. All right, that is chapter 10, day 4. Good luck.